We are going to take a deeper dive in looking at how IMFs affect the physical properties. So, we're first going to look at solubility, melting point or boiling point, and the surface tension. So, with solubility, like we said before, like dissolves like. So something that has dipole-dipole forces is going to dissolve something else that also has those dipole-dipole forces. Something that only contains dispersion forces is going to dissolve substances that only have dispersion forces. The melting point and boiling point are really affected by the IMFs. Boiling is the process of taking a liquid where the molecules are pretty close together and completely separating them into a gas where the molecules are super far apart. So, if it's very easy to separate those molecules, then you're going to have a low boiling point. If it's very hard to separate those molecules, then you'll have a higher boiling point. And the same is going to be true with melting as well. So, the stronger the IMF, higher your melting point or your boiling point. The weaker the IMF means you're going to have a lower melting point or boiling point. Surface tension is going to follow the same pattern. The strong IMF, the stronger the IMFs, you're going to have a higher surface tension. Weaker IMFs or weak IMFs are going to give way to lower surface tension. And that's why if you're playing around with a lot of liquids, some of them you would be able to balance a paperclip on top of, and some of them you wouldn't. And it has to do with the IMFs. So let's look at some practice problems with this. Which of the following molecules will have the highest boiling point and the lowest? So I can look at the IMFs first. What I notice is that all of these contain hydrogen, but only one of them contain fluorine. So that fluorine is going to cause hydrogen bonding, which is the strongest IMF. So for that reason, the HF has the strongest IMF. So it is going to have the highest boiling point. Of the other three, HCl, HBr, and HI, they all have similar IMFs. They all are dipole-dipole. So then you have to look at size. HCl is the smallest, so it is going to have the lowest boiling point. Which of the following molecules will have the highest boiling point and lowest? So for these, I have similar molecules in size in the sense that it's carbon with four things around it or three things. So I really need to look at the Lewis structures. So I'm going to draw the Lewis structures of these first. For this first one, we're going to have hydrogen in the middle surrounded by three hydrogens, or sorry, carbon in the middle surrounded by three hydrogens and a fluorine. So this is going to be a polar molecule. We don't have a lone pair on the central atom. However, we do have different atoms surrounding it. Methane, CH4, is going to have four hydrogens around it. This is going to be a nonpolar molecule. I have my central atom surrounded by the exact same atom. Formaldehyde, we've looked at a couple times already in this video. and it's going to be a polar molecule. Finally, methanol is going to have my carbon in the center. We're going to have the three hydrogens, but now of OH coming off. So this OH is going to be capable of hydrogen bonding. So out of all of these, the strongest IMFs present are going to be in D. So D is going to have the highest boiling point because it has the strongest IMFs. To find the lowest boiling point, I would just look for the molecule that has the weakest IMFs, and that is going to be B, methane. And it has the lowest boiling point because it only contains London dispersion forces. Both A and C are polar molecules, so they will have London dispersion forces in addition to dipole-dipole forces. D is the only one that contains all three IMFs. When you start making solutions and having different molecules or compounds and molecules mixed together, different things can start happening with your IMFs. So if you dissolve a compound in a solvent, in a polar solvent, you can get something called an ion dipole force. And the ion dipole force is going to happen very similarly to the dipole-dipole force, where the anion, the negative ion, is going to line up next to the partially positive side of the molecule, and the cation is going to line up next to the partially negative side of the molecule. If this molecule happens to be water, you're dissolving your ionic compound in water, then the anion will line up next to the hydrogen and the cation will line up next to the oxygen. If you are mixing two molecules together, then you can get what is called a dipole-induced dipole force. A dipole-induced dipole force. So if your molecule is dissolved in, if your nonpolar molecule is dissolved in a polar solvent, then you can get this shift of the electron cloud. When the partially negative side lines up next to the oxygen, right here, it's going to shift the electron cloud in the oxygen molecule away from the negative side of the molecule, and we get this induced dipole moment. Oxygen by itself will have this evenly distributed electron cloud. If you put it next to a very polar molecule, then you get this movement of the electron cloud and that induced dipole moment.